Hello and welcome back. This is Lecture 5 from the Simulating Neurobiological Systems course. That is Systems 556/750, taught at the University of Waterloo in the fall term of 2021. Today, what are we going to talk about? We're going to talk about feed-forward transformation. What do we mean by that? Today we're going to be connecting neurons together. So far in the course, what we've really focused on is just, all right, I have a bunch of neurons, they have some activity. I don't know how they got that activity. Some current was injected into these neurons. They've got some firing activity, so I can inject some information into these neurons, and then I can look at the firing activity and I can decode information from that. So that's what we've done so far, but that's just involving neurons. So far we haven't actually connected any neurons to each other. So let's do that now. And given what we've done so far, what would connecting neurons actually mean? Well, this is the sort of picture we're going to go with as sort of the simplest possible way of thinking about connecting neurons together. I've got some group of neurons A. And they're, and from what we talked about before, when you have a group of neurons, it's going to represent something. So this group of neurons A might be representing the variable X. And I might have this other group of neurons representing B, another group of neurons B, and it might be representing a variable Y. Okay. And the idea is going to be, well, the simplest way that we can connect one group of neurons to another group of neurons is just, I've got some weight matrix W, and that weight matrix, that's going to say how strong the output from one neuron is going to affect each of the neurons in the other population. This is a sort of the standard way people connect neurons together in neural networks. And what the idea is going to be is, well, hold on a second. If this group of neurons are representing X and this group of neurons are representing Y, well, once we've connected these up, well, now the activity in this group of neurons is going to drive the activity in this group of neurons. So what that should mean is that as we change what X is, as we change what this group of neurons is representing, that should cause this group of neurons to represent different values. So that means as we change X, we're going to change Y. That's going to mean Y is some function of X. Okay, so this is what we're going to be trying to build up is at the high level, when we're thinking about vectors and things being represented, Y is going to be some function of X. We're used to thinking of that when we're doing sort of math sort of things. And the idea is going to be is there's going to be some relationship between the function that we would like this system to compute and this weight matrix. And our goal is going to be to figure out a way of, if there's some particular function I would like the system to compute, I want to find out what the weight matrix is that will do that function. So we're going to call this transformation. And one way to phrase that is just that, okay, connections between populations are going to transform variables. So if I've got X here, we're going to do some transformation on X, and that's going to turn it into Y. So these transformations are just functions of those variables. And again, we're starting with the simplest possible sorts of ways of connecting neurons together. As with everything in this course, we're going to start with the simplest thing. Down the road, we might sort of add in more complicated ways of connecting neurons together, and that'll, of course, change the class of transformations we can do. But we're going to start here with sort of the simplest way possible of connecting neurons together. And it is also important to point out that what we're doing here is kind of weird. So it's not the standard way that people think of building connection weights between neural networks. A lot of times when doing neural network work, what people will do is do something like, oh, let's randomly generate some connection weights and then apply some learning rule. Okay, so in backpropagation learning, that's what's happening there. Lots of other sorts of learning rules. The idea is that, we'll just have some learning rule and, run it for a long time, and eventually we'll get the connection weights that we want. That's great, and we're going to talk later in the course about how to sort of combine that sort of approach with what we're going to talk about today. But what we're going to talk about today is sort of an alternate method that just sort of generates the weight matrix that does the best job of what we want. Okay? It doesn't make any claims about how that weight matrix came to be. Again, if I want to have a model of the entire developmental process of a brain from a zygote up to a full working brain with all of its connection weights, cool, then I would need more theory. I would need something that actually says, okay, where do these weights come from? But most of the time, I don't want to generate a full theory of the entire development of the brain from nothing up to a full brain. Instead, what I'm going to want to be doing, or at least one thing that this technique allows me to do, is just simply say, look, somehow there's going to be some developmental process, or either there's some sort of learning process and I'm just worried about the end state of that learning, or I can just simply say, look, let me find the best possible weights, and that can be a good model of my biological system. If the best possible weights aren't good enough to do something, well then, clearly, if there was, no matter what learning rule you had, whatever learning rule you come up with can't do better than the optimal. So we're going to start by let's just generate the optimal weights. But it is worth noting that that's a very different way of thinking about neural networks than people are used to. So people are commonly used to the idea of, hey, look, anytime you have a neural network, you automatically want some sort of learning rule. We're challenging that hypothesis here and just simply saying, look, there are situations where we can constrain the problem well enough that we can actually solve for what is the best possible weights. What that constraint is going to be, so the situation that this is going to work in, is it's only going to work if you're willing to make a hypothesis about what function you think it is that's being computed between two groups of neurons. Okay. If you're not willing to do that, so if you are just simply saying, look, I don't want to make any hypothesis about what's going on inside a giant brain model. The only thing I want to make hypotheses about is about say the input and the output, and then just want some learning rule to go and learn everything in the middle. That's closer to what happens in traditional deep learning. What we're doing here is we're saying, hey, look, as an engineer, if I have some big, giant, complicated problem, I can break it down into smaller parts. I can take those parts, figure out what the optimal connection weights are to do those parts, and then build up my whole model that way. Okay. Both approaches are valid. Both approaches are great things to do. Depends on on what you want to do and what the situation is. But I think it's important to point out that you don't have to do the deep learning approach if you are willing to start making claims about what's going on in the middle, and that's exactly what the neural engineering framework lets you do. Okay, that was lots of fun preamble. What is it that we're going to be doing here? All right, well, so far we've really only talked about one population at a time. I want to start thinking about two populations of neurons. I'm also going to sort of draw, sort of in a slightly weird way, what we've been doing so far. In this diagram, for everything I'm going to be talking about here, whether or not it's spiking neurons or non-spiking neurons doesn't matter. I'll be showing all the examples with spiking neurons. But what we've done so far, we have some input variable x that's changing over time, and it's some d-dimensional signal coming in here. And then each of these is an individual neuron. Okay. And so far what we've been doing is we've taken that input x, we've been doing the dot product with x and the encoder for that neuron. So that's the x dot with e, the thing that we are often writing in angle brackets. We're multiplying by some gain. We are adding some bias. That gives us the current that's being fed into our neuron model. the neuron model is producing some spikes, and that neuron model is then being passed through these decoders. All right, so we take these spikes. Sorry, we're taking the spikes. If we have spikes, and we're often also convolving those spikes with a low-pass filter in order to produce the synapse, in order to produce the actual current that's caused by those spikes. But in any case, those are all still scalar values. The scalar values all get multiplied by some decoder, and that gives me my estimate for x. Okay. That's basically what we did for the last 3 or 4 lectures. Fine, I'm just sort of drawing in a slightly weird way. So that's one population. Well, let's say I have 2 populations. Fine. All right, I just made another copy of that same picture. Of course, this one's getting y being passed in, and some other neurons. Okay, so I've just made 2 copies of what we talked about so far. So what? So let's take a closer look at those neurons, because each of those neurons has a different gain and different bias, and if we wanted to, we could go take a look at what their tuning curves look like. Okay, so say like maybe this is the one randomly generated set of tuning curves for one group of neurons. It's population A. As x changes, different values, those neurons are firing at different rates. Same thing for B. Different neurons. In fact, there's a different number of neurons. I've got 21 neurons in this one and 22 neurons in this one. They have different tuning curves. So that's going to mean that as I feed in a value x, if I feed in a value x to both of, if I feed in the same value to both of those groups of neurons, the neurons are going to have different spiking patterns. Right? They're going to have different activity because each of those, there's a different number of neurons, so of course they're going to have different spiking patterns, but there's going to be different activity out of each one. But I can still decode it in the same way. And so if I feed in some value, that's this black dotted line around here, feed that value, that same value, I feed it into both of those groups of neurons, I'll get different activity in those 2 groups of neurons, but then if I decode out a value, I'm going to get something pretty similar. Right. That's just doing 2 copies of everything we just showed in the previous lecture. So one key thing there is I just wanted to highlight that different neural activity might encode the same information. Because I've got this neural activity, I've got whatever neural activity is caused by these tuning curves and whatever neural activity is caused by these tuning curves. Different neural activity, same information being represented. Okay, fine, nothing too weird about that. Let's say I want to connect these up slightly differently. Let's say I build this thing, decodes out some estimate of x, and then I compute some function on that estimate, and then I feed that into this other group of neurons. That's closer to what we want. That's really what if we want to have groups of neurons computing something, then we can sort of imagine, okay, if I decode out some estimate of x, and then I compute some function on that, and then I feed that into a group of neurons. Okay, cool, that's kind of what we're looking for. That would make this group of neurons compute some function of x. But it seems a little, that's, whatever this function is, that seems like, oh, like there could be some really complicated functions in there. Let's start with something simple. Let's start with y equals x, just as the simplest possible function. Okay, so I just want this group of neurons to represent the same thing as this. Okay, can I make this look like that first picture that I showed of it's just connection weights between neurons? Because staring at this, I mean, this does not look like just connection weights between neurons. There's a whole bunch of steps in here. What would be the biological correlate of each of these things? There is no sort of, when I connect 2 groups of neurons, I don't have something like, oh, all the connections coming out of one group of neurons goes into something, and then that one thing goes over to a whole bunch of other neurons. It's just not what you see biologically. The closest thing you might see is just, oh, hey, like that big weight matrix I was showing at the beginning, that, hey, look, these neurons are connected to these things, right? So what can we do about this? Well, first of all, we can actually just try doing exactly what I showed there. Let's ignore biological plausibility for a moment. Let's just do the math as we've been showing here. And we're like, okay, fine. This is what I was showing before, where I just fed the same value into both groups. But now if I do the math that I was showing before, I get this. Okay. So there's no change to the blue line, of course, because that's our first group of neurons, and we're still feeding in the input to that. And you can sort of see that orange line, that second line, we're getting a slight shift to the right, or there's a slight delay happening. Right? That's a little bit later. Okay. That delay is actually just due to that low-pass filter synapse model that's being applied in here. That each spike is being turned into one of these little exponential decay things. And so that is causing a little bit of a delay. Again, that's also a side effect of the fact that we made our filters causal. One of the things that we were talking about in the last lecture. But the idea is there, we're passing the information from one group to another, so this math works out fine. So, like, if we, it's not biological, but we can make this estimate of x, and then feed that exact value into this next group. Okay? And we don't actually lose much information. Like, it's other than that little bit of a delay, we're getting pretty much the same result as if we had have just directly fed x into both of these neurons. But it's not biologically plausible. So how can we turn this into something that's biologically plausible? Well, let's just reorganize this a little bit. These dot products that are happening here, that's another way I could write a whole big chain of dot products, right? And these ones here. I can just write that as a matrix, right? Taking this input, do a matrix, multiply, and then feed those values into each of these plots, right? So those are identical. I've made no change whatsoever to the math that's happening. We're just writing it differently. That gain factor that we've been putting on the input each neuron, well, that gain factor, well, I could also pull that gain factor into this matrix. Right, that's pretty easy. And that's happening there. Well, I'm also doing the same thing here. Fine. Okay, so now what have I got left? I've got a neuron model. I've got some bias going into my neurons. Okay, that's fine. That's just some background current being fed into neurons. That seems okay biologically. Now what do we got in between here? I've got my output from my neurons being multiplied by some matrix. That gives me my value x hat. This y equals x thing, well, that's not doing anything. That's just identity, so that's not doing anything. This isn't doing anything. This is just another matrix multiply. So I've got a matrix multiply followed by a matrix multiply. I can just multiply those together. And all of those steps that I just did, none of those were even approximations. All of those steps were just mathematically identical. So there is no difference if I generate this weight matrix by generating this and multiplying them together. Now, and again, this E thing, that's our randomly chosen encoders for each neuron. This alpha is the randomly chosen gain for each neuron. This D, that's the solved for decoder. So the thing where we're looking at the spike data and we're going, okay, what's the best possible way for us to interpret this data? So this D thing is something that we calculate, but the E and the alpha is something that we just randomly generate. We take these things that we randomly generated and this thing that I calculated, and I multiply them together, and I get the weight matrix that is exactly the weight matrix that we wanted. If I go all the way back to the first slide that I was showing, it's exactly this weight matrix. This is a very strange way of generating a weight matrix. Okay. I'll also sort of highlight, I mean, this decoder, when I go and generate this decoder, I haven't even thought about population B yet. I generate this decoder only thinking about population A. Right? And when I generate this, the alpha and this encoder, I'm only thinking about population B. Right? So I don't even have, like, when I'm generating these original matrices, I don't even have to think about other groups of neurons. I just have to think about the one group of neurons that I'm worried about. It only is then time, once I've generated all those matrices, if I want to generate the weight matrix between neurons, I just multiply those two things together. And again, everything is mathematically identical whether I do it this way or this way. Weird. If you went and do that, you would of course get exactly, exactly the same graph that I was showing here. We're going to be able to use that weight matrix to pass the information from one to the other. Has to be exactly the same math. Just, I mean, we haven't done any approximation. So just we'll get exactly the same result whether or not you do it this way or do it this way. Modulo some rounding errors due to the fact that we don't have infinite precision on our floating point values. So there's going to be some tiny, tiny, tiny little difference just because of how well our computers are representing those weights. Cool. So this is a method for generating weights that lets us pass information from one group of neurons to the next. We want to do more than pass information. We would really like it if we could compute arbitrary functions, right? Because so far I've sort of just done, I started saying I would like some function of x here, and I just did the special case of y equals x. The special case of y equals x, well, that's sort of what let us do this trick that I just described, right? Because that's what lets us, the fact that we're not doing anything here, that's what lets us take that decoder and this and multiply them together, and everything should work exactly how we want. What if I want an arbitrary function? Now, a couple possibilities here. There's one special case that we can actually just read off of here, and we can say exactly what we do with it. If this function is a linear function, okay, so if this function is take x and multiply it by something, by a matrix. So if x, because remember x could be a vector. So if I take that vector and multiply it by some matrix, if that was the case, then I would just have a situation of, well, I have this decoder, I have a matrix multiply here, and then I have another matrix here. Cool, now I could just combine all of those together into one weight matrix and get my weights. So that would do exactly the same thing. Okay. So for any linear function, cool, I can do exactly the same trick. I just get an extra matrix that I'm going to put here, and I just multiply everything together and to get my main weight matrix. All right, fine, that's linear functions. I'd like nonlinear functions as well. And that feels a little bit tricky because I can't just, if this is a nonlinear thing, well, now I can't do this trick of combining a bunch of matrices together and getting one weight matrix. So we have to do something slightly new. And that thing that is slightly new is, well, hold on a second. The way that we got this D matrix, right, we found the optimal decoders that found some estimate of x. We didn't have to find decoders that were some estimate of x. We could find decoders that estimate some function of x. What's that mean? Well, when we did that solving for the decoder, right, we had to feed in this x, here's the target values. Right? That's when we were solving the decoder. We were saying, okay, find me the decoders that if I multiply by my activities, I get these target values. And when we did all that math, we chose the particular target values that were the same as our input. Right? We put x here. Nothing says I have to do that. I could pick something else here. I could generate y that is just some arbitrary function of x. Right? Whatever function I feel like. Right? Do the same math, find the decoder. Notation-wise, we're going to write this as an exponent, which is a little annoying. It's not actually, maybe a subscript would have been clearer. We've just fallen into the habit of writing it as an exponent. So this is the decoder that approximates the function f. This is the way that we write that. And the way that we generate this y, it's just simply, okay, take all of our x values, the sets of samples that we used to generate our activities, compute whatever function we feel like on each of those x values, and that gives us our y matrix. That gives us a decoder that approximates that particular function, and now everything's fine. Now I can just take this decoder, multiply it by this encoder, and everybody's happy. Okay. What this gives us is a general method for making a set of connection weights that will approximate whatever function I feel like. Okay? I still have to decide what function I want, and I have to decide what my neuron properties are like, what neuron model I'm using, so what my tuning curves look like. Again, these are all things that hopefully we can choose based on the biological system that I'm modeling. This function, basically what that's going to sort of come with is if I have some hypothesis about what I think this group of neurons is computing, or if I have some large task that I can break down into a bunch of subtasks and say, okay, well this is the individual functions that need to get computed. That's where I would get that, and now I can build up my model. Okay. Cool. How well does this work? So first thing we can sort of look at is how accurate can this decoder thing be? Okay. Because this is something slightly, we've looked before at, well, how accurate is when we're decoding out x, right? And we saw that as we increase the number of neurons, the mean squared error drops as like 1/n. What happens as we put in arbitrary, because I can put some arbitrarily complex function in here. Can it do anything? What are the limits about what sorts of functions this sort of system is going to be good at approximating? Okay. So we can try that with a few different functions. Okay. And here we're trying it with just sort of 10 neurons, just as an example. And again, we're just focusing on this decoder part. I've just got 10 neurons. Here's the randomly generated tuning curves of those 10 neurons. If I try to decode out the function just f of x equals x, this is the identity functions, this is what we had been doing before, right? You get some error. Okay. Fine, solve for my decoder, I get that. But again, using the technique that I just talked about, nothing stops us from, let's just find decoders that do other functions. Right? Again, the only thing we're doing is we're replacing the x when we solve for the decoder with y, where y is we just take all of our x samples, compute the function, that gives us our y. Okay. Cool, so how well does that work? Well, let's try x squared. Well, it actually works not too bad. Okay. It's not perfect. Any more than this was perfect, but we can do it. Sine of pi times x, so that's a sine wave here. That's a little iffier. Absolute of x, it's got some difficulties here with this really sharp change here. Some sort of really nasty, so here's a step function, so All right, step function, woo! So the dotted line is sort of the ideal step function. The blue line is what happens when we try to find that optimal decoder. This looks like it's doing particularly, it's still doing something like what we want, but it seems to have more error for this. So there's something about this sort of function and this sort of function that make them particularly hard to do, and something about this sort of point here that makes this hard to approximate. All right. In a later lecture, we're going to get a little bit more detail. Yes, we can sort of analyze this and figure out, can we actually characterize what it is that's hard about these functions? For now, what we're just going to do is point out, well, if we crank up the number of neurons, here's 20 neurons. Oh, all right, we get better. Right. Here's 50 neurons. We get better. This is starting to work pretty well. That's pretty good. This one's still pretty hard. 100 neurons. We're doing pretty good. Again, there's certain points that seem to be very difficult. But it's still doing something kind of nice. I've asked it to do this sharp step function. What it's ended up approximating is a slightly smoother version of that. Okay. Of course, in the limit, as you crank up the number of neurons to infinity, yes, you can get it as accurate as you want. Hopefully you don't need an infinite number of neurons. But that general approach of as you increase the number of neurons, your error should go down also applies in this sort of situation. Cool. So that's going to let us build neural networks that approximate arbitrary functions. Okay. We can generate some weight matrix. We can do it using the approaches that I've just said of taking the encoder or computing a decoder for that function, taking the encoder that generates the tuning curves that we want from this population. So I will note that in these notes, we sometimes fall into this habit of sometimes writing the alpha and sometimes not writing the alpha. Anytime I haven't written the alpha, it's because I've already pulled the alpha into the E matrix. Sorry about that. I should be better about that. But in any case, we have this weight matrix. Everything's all fine there, and we can do this for any population, or for any function that we want to approximate. And this gives us a way of generating the weights that'll do that. Cool. That lets us do one function to compute and sort of have this sort of chain of one population into the next population into the next population. What about combining things in a slightly different way? What if I have x and y in two populations and I want to compute something that is some function of x, or that is some linear combination of a function of x and function of y? That turns out to be nice and easy. So just if you work through the math of what we've just done there, if I just make two versions of those inputs, maybe I can sort of show it this way. If I had two copies of this thing on the left, and I fed both of them, and I sort of did a linear sum of them here, all right? So that would be a sum of whatever some function is computed, and another one computed by another population, and I summed them here, and then fed that into y, and went all over here. Then clearly population B would be the sum of whatever function was extracted out of this one, and whatever function was extracted out of the other one. And if you do that sum that way, it's pretty clear. But then if you follow through that same approach of, well, just make this as a weight matrix, then we're going to get this situation where we generate one weight matrix coming out of this first population. We generate a weight matrix that computes some function out of that. And then we have another weight matrix that is coming out of this population. And the total current going into each neurons is just the sum of those two. Just because everything's linear, and everything I've just drawn there, the value being represented in this next population is going to be the sum of whatever these two things we're feeding in. Okay. So that means, again, let me try that again. If I generate, so each of these circles is a population of neurons now. And this population is representing X, this population is representing Y. This arrow, this one single arrow, I'm using to describe this whole situation here, where I'm generating some weight matrix to compute some function. And I'm generating that weight matrix by having the decoder by solving for the decoder that computes that function and multiplying it by the encoder for my second population. If I do that twice, I have two different inputs to this one population, then this group of neurons is now going to represent this sum, okay? Just because everything is linear. So again, I'm solving for this. This connection here is solving for the function f1 of x. This line here is my set of connection weights that's solving for the function f2 of y. This population, maybe it's called z, is now going to represent f1 of x plus f2 of y. Okay. So I can use this approach to now build up sort of linear superpositions of functions. Does that let me do anything, any sort of computation that I want? Yes, but we got to be a little careful here, because there's one thing that it looks like this doesn't let me do. What if I wanted this population here to represent x times y? Well, that seems like a reasonable thing that I might want to compute. So I have x represented one population, y represented another population. I would like to have another group of neurons that represents x times y. I can't write x times y in this form. Right? It's not some function of x. It's not a linear combination of some function of x and some function of y. So it feels like there's no way to compute x times y with this approach, if x and y were in different populations. Now, of course, if x and y were in the same population, if I had some vector that was x comma y, and I had some group of neurons that was representing x comma y, well then sure, there'd be no problem at all decoding out of that the function x times y. Right? That's just, that would just be exactly this approach that I've already shown. Right? It's just, because again, what I've just shown here, x can be any arbitrary size, y can be any arbitrary size, and f can be any function I want. So no problem at all doing x times y as that function. But I don't have that case. I don't have the situation in this where x and y are in the same population. But I do have this trick where I can do some linear superposition. So if I want to compute x times y, or any other arbitrary function of x and y that can't be written as a linear superposition, well then all I do is I'm going, okay, well if I have one population representing x and another population representing y, I'm going to need this other population to represent x comma y. I can write that as a function of this form. Okay? I make this connection here. The function being computed is, all right, so let's say x and y are scalars for this example. All right? The function being computed is now taken in a scalar and output that scalar comma 0. Right? That's a function. It's a weird function. It's not a common function that we're used to playing with, but it's still a valid function. I can solve for that connection weights using the approach that I've just seen. If I do this function for this one, 0 comma y for this thing, connect up all those connection weights, right? Now this population here will now have in it, because of this property that we just talked about here, this population will now have in it the vector x comma y. Now from that, I can compute out whatever this arbitrary function is that I want. So x times y or some other nonlinear function. What we're now doing here is we're saying, hey, if my neurons are representing information in a particular way, so if I have neurons that are representing x and y separately, This is making a claim that I need an intermediate group of neurons that are representing both x and y in order for me to compute some nonlinear function of x and y. And I now can use this technique to generate both of these sets of weights to make this all happen. Okay. To somewhat compare this to what people are used to, maybe if you're familiar with backpropagation neural networks, this is a variant of the XOR problem. So in backpropagation neural networks, one of the standard problems is, all right, I have x and y. They don't tend to think of it as the product of x and y as the output, but the XOR of x and y. But again, it's a nonlinear function of x and y. And one of the sort of core principles of deep neural networks is, hey, if you have a function like XOR or a function like multiplication, you can't do it by just connecting your inputs to your outputs. You need to have a hidden layer. And then traditionally what you do is you do the backpropagation learning algorithm in order to learn the connection weights here and the connection weights here that are going to make that work. What we're doing instead is saying, okay, well, you know, for this case, I don't need backprop. I can just go ahead and just find the connection weights that are going to make this work by math. Okay. In order to do that, I need to make some claims about what I think this hidden layer is representing. In general, yes, backprop. You know, because when we generate these connection weights, or generate this neural population, if we're constrained by biology, if biology is telling me what these encoders are and what these tuning curves are for these neurons, cool, all right, then we're going to be solving for the best thing. If I don't have any biological data, then I might do backprop across all this in order to find those weights, or I might just use the techniques that I just talked about here to generate these weights. They're both going to give fairly similar answers. In general, what's going to happen is backprop can improve things a little bit over this whole situation, but they're pretty close in terms of accuracy. And I will also point out that, you know, this can be a lot faster, especially as we get to larger and more complicated things. Doing this analytic approach of, oh, I know what this intermediate group needs to represent, can let me analytically solve this much faster, okay, than doing backprop. And again, later on in the course, we will sort of talk about, for the particular special case of multiplication or things like that, you can actually start figuring out, well, what would the best encoders be? Instead of randomly doing my tuning curves, I can do a better job. And then we do actually end up with the same answer that backprop would give us, but analytically rather than, yeah. Cool. All right. So this is what lets us sort of start building up larger systems. I will also point out that this is also a situation where, as you start making more complicated neuron models, the statement I've made of, oh, hey, look, you need an intermediate group of neurons, starts to be a little bit more flexible. It does turn out, and you know, Andreas Stockel in the lab, actually the person who put together a lot of these slides, has been doing a lot of interesting research on, well, what happens if I make the dendrites of my neurons a little bit more complicated, and it turns out that as you add in that complexity, there are certain functions you can now compute without having that hidden layer. So we'll have a class on that later in the course. Again, just to sort of see some examples of this, here is this sort of linear superposition situation. I have a group of neurons X, group of neurons Y. I feed in an input to X and an input to Y. If I decode that value, sort of just exactly the stuff we were doing before this lecture, then I get these two curves. I generate these connection weights. I decode the value coming out of these spikes, coming out of this activity here, and we get this line, and that black dotted line is the sum of these two. So the black dotted line is sort of the ideal addition of X and Y. and the green line is what we actually get. So just sort of showing this approach seems to work. Is there anything else I want to say about? Yeah. So the math I just showed you works as expected. One particular nonlinear function that I was sort of commenting on there that sort of seems to be really, might be very useful is multiplication. So if we're wanting this particular function here being computed to be x times y, now we can do something like, okay, well here's our two inputs, so same, this sort of same network structure. I'm just putting on this sort of extra output. And solving for the weights, approximating different functions. And I'm feeding in one input, which is this blue line, feeding another input, which is this orange line, and I can get this green line out. And again, now we're sort of, okay, maybe I might want to add a few more neurons here to make this a little bit more accurate. But the ideal output is this black dotted line. We can sort of see that just because one of these values, if I'm multiplying by 0, the output should be 0. Fine. All right. Well, when I multiply by 0, my output's 0. When I multiply by 0, my output's 0. Not too bad. When I multiply by 1, then my output should be the same as my blue line. All right. That seems not too bad. If I multiply by 1, that seems to be working. And then, of course, when I multiply by -1, then things should be flipped. It goes up, this goes down. So we can do that. Again, increase the number of neurons. You can change around its accuracy. The reason I want to particularly highlight multiplication is as we start building up more complicated things later in the course, or more complicated cognitive systems, multiplying seems to be a really useful thing for lots of different representations. So for instance, if I have multiple signals that might need to be sent to one particular part of the brain, but I don't want all of them there all the time. Sometimes I want one value and sometimes I want a different value. I can do multiplying, multiply everything by 0 except for the one that I want to keep, and then that one I multiply by 1. That's a really effective way of controlling the flow of information from one part of the brain to another. It's also something that sort of seems to be tied to a lot of attention sort of thing. So people, when they're modeling attention, they might do something like, okay, if you're paying attention to how bright something is, I might multiply that by 1. But if I'm not paying attention to the color of it, I might multiply the color by like 0.1, and that might make colors less important, or sound, or things like that. That's a sort of a very common way that people have thought about doing attention in the brain. It seems to map very nicely onto this. As we get into how do we represent language and things like that using the framework that we see there, will turn out that multiplication will be the basis of how we sort of bind information in sentences together. And then statistical the multiplication shows up in lots of different places in math, is really all I'm saying there. And multiplication turns out to be something that we sort of very frequently will want to do in these sorts of models. But of course, there's nothing special with multiplication. There's something a little special about multiplication. Multiplication, when we do the course on, okay, well, what functions are we going to be good at? When we do the class on what functions are we going to be good at, multiplication of two values is going to turn out to be a lot like this x squared function, where we're like, okay, we're not quite as good as that as we are at a straight line function, but we're still pretty good at it. Cool, so that'll be useful. Cool, so that is the basis for how we're going to connect groups of neurons together. And that's going to let us start to build large-scale cognitive models. There's still an important step that's going to be happening next, though, because all of the connections that I've shown so far are feed-forward connections. The one step that's going to happen next is, well, what happens if I do exactly the same math that I just showed, but allow us to do recurrent connections, so connections from one group of neurons back to itself. That's going to let us start doing something new that we can't do with any of the things I've shown so far. Because everything I've shown so far, the output is a function of its input. Okay? And there's no sense of storing information over time. There's no sense of there's no sense of time in what we've done so far. The moment we start, if I have a purely feed-forward neural network, well then whatever the output is has to be just dependent on whatever the input is right now. The moment I add in some recurrence, that's going to open the door to new sorts of things, and we're going to need some way of mathematically characterizing that. Okay? But at the moment, we've got a system that we can do any arbitrary functions, as long as they're functions of our input. Cool. So we will see that next. Thank you, and we'll see you later.